Hello. Good morning, everyone. We're going to get started on time. We're having announcements at this point, so you're not going to miss any of Jim's talk. I was given a long list and several others snuck into my pile as I was walking up here. Don't forget to visit the art exhibit. It's inside the hallway and off back towards the outside. Wonderful art pieces, wonderful student art. You can vote for your favorite age group of student artists, 2 each. Be sure to do that. It's just a really nice experience that we're having at ASLO this year. Again, we have TikToks this afternoon starting at 1:30. Please plan to be present for that. Today's session is on geo-engineering of aquatic systems, and the plenary this morning will feed very well into that. There's a poster session and reception beginning at 6 in the exhibit hall. Have your name badge. ASLO's hosting a champagne toast this evening at 7 in the ASLO booth to launch the newest limnology and oceanography ebook, and Steve Smith is here and would love to have you be there. Poster presenters, take your posters down between 7:30 and 8:30 this evening. ASLO's undergoing a strategic planning process. President-elect Jim Elser, down here somewhere, will be at the ASLO booth during the poster session, ready to receive your wonderful and great ideas of how ASLO should progress into the future. And I understand that John Downing is giving out prizes if you make a good contribution to the idea pool. So I'm going to be there and I'm going to have all my good ideas, and John's going to give me something. That'll be nice. We also have the research vessel Pelican from Louisiana University's Marine Consortium, which is where I'm the executive director. It's down on the dock. If you walk between here and the riverside, you can see it, see the white superstructure, but you can't really get to it that way. So you have to go down, go out the convention center, go along the road walk, and then I think over the train tracks or come in the other direction, and you can have a tour of the Pelican. We've got school groups today going through in the morning, and it's open all day. Just come and visit us sometime. I think we'll be very pleased to show it off. The reason we're here this morning is to hear yet another plenary speaker for the ASLO meeting. We've worked very hard on getting the top-notch people in limnology and oceanography here at the meeting. Those of you who know Bob Mead from the USGS know that he's Old Man River, and I'm not going to call Jim's Syvitski Old Man, but he is like Dr. Rivers. This is plural rivers. This is not just one river. And so we're really pleased to have him here. He's been contributing to the understanding of rivers on a global scale since being at University of British Columbia, and he has, so that's 3 decades now. Maybe you are getting old, Jim. To study this, he's now at the University of Colorado, where he's the executive director of CSDMS, the Community Surface Dynamics Modeling System. My first interactions with Jim, we don't have to tell all these stories, was when I was in LOEX as a member of the Scientific Steering Committee. And he's gone beyond LOEX now. He is now the head of the chair of the IGBP, the International Geosphere-Biosphere Program. He's received many rewards in his past, and those are listed in his CV in the program. But it's my strong pleasure, great pleasure, to welcome Dr. James Syvitski to the podium to share with us his knowledge of geo-engineering of lowland, floodplains, and deltas. James. Thanks.
Wonderful. Okay, thank you for getting up so early. I just flew in from India, which is why I'm a little ragged, but in India it's 8:30 at night. So I grew up on a delta, and I submitted my first thesis in 1975 on a delta, so it's almost 4 decades ago. And so this talk is about geoengineering, and we know about geoengineering from the perspective and debates that are going on about what we can do to fix our greenhouse gas addiction and trying to get some of that CO2 and methane and other greenhouse gases out of the atmosphere. So it's engineering at a big scale so that the planet changes. So this talk is about hydrology and river systems flowing into the ocean and the geoengineering that we have been doing for the last number of years, decades, centuries. And I'd like to acknowledge, as Nancy has done, ASLO's invitation and my 2 sponsors, CSDMS and IGBP. So let's begin with the Indus Delta. This is an image of the Indus Delta. It's, I don't know, 800 kilometers in its length profile, maybe 1,000 kilometers. And you see on your left maps of where the river was in the 19th century. And you can see that this is a river system that would shift its pattern of flow. And if you look at where the distributary deltas entered the ocean, there were many of them and they shifted around quite a bit. So this is a natural system. On the right, you see, well, it's hard to see on that slide, but it's quite bright. But there are some hairlines that show 30,000 kilometers of canals system. That's replaced these tributaries and distributary channels so that now there's really only one main channel that flows to the ocean. So this is the beginning of what I would like to call geoengineering. And let me go back. So if you look up here, this is the town or city of Syvitski. I'm going to show you the barrage that takes some of the water from the river system . And so you can see that you now have where the river would have once flowed down here, it's getting taken away from the main channel into these large canal systems. This has great impact to the river itself because rather than letting sediment come down through the system, it aggrades here. And the 2010 flood that displaced over 10 million people was because of that. So here's another slide. This is of the Po River system. And I'm going to walk you through how we've engineered that system. And again, I guess when I prepared these slides on my Mac, they look a little different on a PC. But there's the town of Bologna. This is 1000 BC, and this is what the coastline was. There was a series of river channels that came down the Po Valley, and these rivers would shift around, and so that you ended up without a delta. This is a very natural system. The rivers followed the line of easy access to the river, to the ocean. But sometime in the 10th century, so 2,000 years later, the people of Bologna, they wanted to get their goods to the town of Venice. So they broke through the river system and dug a canal system. That's an interesting idea they had for their commerce, but because of that, the river actually took on that canal system, took over that canal system, and became a dominant distributary channel. So by the time of the 16th century, much of the river flow was flowing towards Venice. The Venetians they found this not to their liking. It brought too much sediment to the Venice Lagoon, and so they decided to open up the system so that instead of the water flowing towards the Venice Lagoon, it would flow away from the Venice Lagoon. And you can see that by the 17th century, you had the beginning of a delta. They kept manipulating the systems and the whole river channel itself so that you basically controlled where the water and sediment went, and the Po Delta was a creation of humans. So let's move back to Asia. So this is an SRTM image of the yellow floodplain, alluvial plain, and this is a track of where the river channels flowed over the last 3,000 years. Now it's interesting that sometime in the 10th to 18th centuries, China put a lot of their gross domestic product in controlling the flooding of this river system. And they worked on this and threw a lot of money at it, 10 to 15% of their GDP, so that they could control where the river went. Otherwise, many of the people that were living on this 700-kilometer floodplain were getting impacted negatively by these floods, loss of millions of lives. So that they created these hardened levees, and because these levees trapped the sediment, they super elevated the river. So now you ended up, also in this SRTM image, you ended up with a river system that was super elevated to the floodplain. It was 10 to 20 meters above the floodplain. You had a super elevated river. And again, I apologize for the brightness of the screen, but if you can just follow where my pointer is, you have the modern profile across one of these levees, and another one, and another one. This is the old Yellow River system that used to flow into the Yellow Sea, and this is in meters above the floodplain. And so really you have a lot of traffic going on, and they have to keep rebuilding higher and higher these levee systems. Rather than controlling the floods as shown by these circles on the maps, the floods focused around these elevated river systems. Almost every other year, every 2-3 years, the river would flood, and the size of these circles provide you with information on the magnitude of the flood. So by controlling this one river flowing into the Yellow Sea, you had a concentration of floods in this area. And this is the modern river system. It's only been flowing into the Bohai over the last 150 years. This is the new Yellow River, and you can see there's a strong concentration of floods along that river too. So if you were looking at how rivers flood, and you use the yellow as an example, this has nothing to do with nature. This has to do with human engineering. And to emphasize this point again, I have a little diagram here. This is what a river system would normally look like. The bottom of the river channel is below the alluvial plain floodplain. But as you control the river flooding, you aggrade in the system, and you have to keep building up these hardened levee systems. So in the Po, this gives you an example of what's happened in the 20th century. We've had aggradation rates of tens of millimeters per year throughout the delta system itself. So the only high point of the delta is the river system. So another thing that we've done is we've engineered how many distributary channels we have on this delta. So again, just like on a floodplain, these channels would want to migrate around with the different floods, follow the path of least resistance towards the sea, shift around, depositing their fresh sediment load, sediment and carbon and other nutrients on the delta plane. And if you look at the mapping of these channels over the last 19th century, you can see the shifting that would go on in this case on the Nile Delta. Well, this is a problem if you have millions of people living on a delta. You don't want these people to be subject to flooding. So you control where you harden these channels, and often on deltas, you reduce the number of channels. You reduce the number of channels for a wide variety of reasons. One of the biggest reasons in the 19th century was to get ships inland. So you have only one or two really deep water channels you eliminate. So on the Nile, you've gone from 15 channels to 4 channels. And you can see on other delta systems, there is this reduction in the channel system. Here's an example. This is an air photo of the Fraser Delta in Canada. And of course, they built an airport on the delta. And you don't want that airport to be flooded, so you really harden these levee systems. You don't allow any shifting to go on, and that's, again, another example of why you might control nature. So, that's telling you more about the positioning and mobility of these channels. I'd like to now remind you of what we've done to the hydrographs. So let's go back to this map, which shows how much we've stored the river system. And where the dark colors are, we're storing up to 100 or even more than 100% of what that river system would normally carry in a year. We're delaying the flow, and we delay the flows to the ocean by weeks, days, weeks, and for the big river system, months. And that water is stored and getting out into the ocean much longer than they would normally. So we're changing the freshet conditions of most river systems. In the Nile, and this is not uncommon, we want to grow crops 3 times a year. And to grow crops 3 times a year, and basically all year round, you increase the base flow, so there's always water pouring onto the delta system. And the only way you can do that is reduce the floods that would otherwise hit that delta. So you basically end up having a totally controlled, unnatural flow of water to the coastal ocean. Part of the CSDMS organization is we have the Dartmouth Flood Observatory within us. And this is a unit that maps river floods around the world twice a day. Covers the entire globe twice a day and maps their flooding conditions. This is one of the maps that they produced. The delta is the Chao Phraya, Thailand, the city of Bangkok, someplace down here. And all in red for this 700-kilometer stretch is the flooded area from the 2011 flood. This flood, yes, it was related to a weather event. A strong monsoon rain system was hitting the area. But the flood itself had nothing to do with the rain system or climate. In fact, they had stored too much water in the reservoir behind the dam, and and most dam operators want to do that. Water is money to them. they release it in a very economic way. And so storing the water and releasing it is a very economic decision. Well, they had stored too much water in that system the previous year. So when the storm was coming, they feared that they had no capacity to take on that new rainfall, and they released it. And it was an over-release and flooded the entire floodplain. Again, with massive loss, tens of billions of dollars in damage. And so that takes me to this little diagram produced by the Dartmouth Flood Observatory, where they map the flood conditions on the Earth's surface. These are the floods that are greater than magnitude 4, and these are the floods greater than magnitude 6. And in both conditions, from 1985 to 2009, you see an upward tick on the number of floods that are occurring on our Earth's surface. So, these diagrams are well published and well used, but since we generated them, I want to tell you a little bit of little side story. We don't think that they have to do with the intensification of the hydrological cycle. We think this has to do with the failure of the infrastructure on our waterways. Now, this is a speculation on our part. We have not gone back and done a post-mortem on every one of these floods. So, again, as I say, this is speculation. The number and magnitude of the floods are certainly increasing, but every time we've looked at the big floods, there seems to be a strong human influence on why that flood exists. And this is just one of the flood maps of the Mekong Delta. But we are truly on a global scale changing how we use and deal with the hydrological cycle. This is the total water consumption on a per pixel basis in millions of cubic meters per year per pixel. And you can see the strong use of water for whatever our needs are. Irrigation, hydroelectric power, recreation, the list goes on. And this use is at a magnitude that really is at the level of the hydrological cycle. So we really are manipulating the hydrological cycle, at least when it comes to surface flow. You can look at the number of rivers that are being dammed and the number of dams on this axis in 1750 to 2000 here, and you can see this upward tick, and you can see the water use upward tick. And maybe this flow chart of the Indus may help you get a handle on what goes on in a water balance of a modern river system. So the Indus, one of the largest rivers of the world, has 108 units that normally would go to the sea. And the units are cubic kilometers, but it doesn't really matter. 108 units, and only 45 now gets to the sea. And that's because we take this water, we put it on a desert, and we turn that desert into an agricultural land system. And so we're pumping water into the sediment, we're getting it to grow plants, and so there's evapotranspiration, there's evaporation. There's a lot of people that now live on this desert, so there's domestic use, so forth and so on. So this diagram by a colleague of mine, John Milliman, all these red dots are fluxes of water that would otherwise have got to the ocean, but they've been reduced by a magnitude greater than 30%. And you can see that for much of the world's river systems and delta systems, that we are taking out water and we're putting it back up into the atmosphere before it gets to the coastal ocean. At great impacts to the coastal ocean. Some of them may be unknown around here simply because for most of North and South America, we don't see that. In fact, we're taking water from one side of the Rocky Mountains and allowing me, living in the Denver Boulder area, to have trees. And so we're pumping water from one side that would otherwise have flown in the Pacific and putting it in the Atlantic. So let's move on to sediment. Sediment is that great material that creates the deltas in the first place and basically controls the wetlands of the world. And this is a study by colleagues from China and Japan, Wang et al., where they looked at the river system, and along this axis we have in gigatons, thousands of gigatons, we had these 5 main river systems, the Yellow, Yangtze, Pearl, Red, and the Mekong. They were kicking in about 600 gigatons per year to the ocean. And through deforestation, agricultural practice, mining, it shot up by over an order of magnitude. And so that by the mid-20th century, a lot of sediment was getting out to the coastal ocean. So these rivers delivered an extra 2,000 gigatons over the last 1,000 years. Over the last 50 to 60 years, the amount of sediment getting to the ocean has decreased dramatically because of dams. You can see it in this diagram. So, to sum that up, we've added all this extra sediment, which basically created the deltas in the first place, and then we stopped the supply of sediment to the deltas. And you've seen this diagram where once there was around 430 million tons per year entering the coastal ocean of the Mississippi, and by the end of the 1990s, it was down to 240, and the latest studies say that this has been reduced much since then. And to make this point, I have a movie that I call my Matrix movie, and I'm going to ask the folks on the side to play this movie. And you're going to see where the reservoirs are built. You can see the expansion of Europeans across North America. The years are ticking by here. So this is the growth of reservoirs in the US. It's impressive, isn't it? And to give you a sense of what that is like on the ground, I used some satellite trickery, and I've zoomed in on this box over here, and I'm going to let you see what this looks like from a satellite. So it's hard to see, but there's a river flowing down here called the Mississippi, and all these black areas and blue areas are reservoirs. There should be no bodies of water on this land surface except those right near the river system itself. I mean, is that not impressive? So let's zoom in on this area, and I'm going to blow that up, and you can see these blue areas on top of the black. That's where suspended sediment is entering the reservoirs and trapping sediment. And again, we can do this on a daily basis, so we know sort of what the timing of where these reservoirs are getting their sediment. And so that you get a sense that this is not just a US thing, I have created another movie with my colleague Albert Kettner, and I'm going to ask that this one's played. Here, wherever you see a red dot, that's a new reservoir, and these are only the very large dams now. And you'll see the Americans, the British Empire, Japan, and I'd like you to pay attention to the Great Leap Forward in 1950 in China, which within a few years created almost as many dams in China as we had in the US over the last previous 150 years. And what is a large dam? A large dam is any reservoir above 100 or 15 meters. And so these are the very large ones, and these large ones have the greatest impact on water and sediment. To put this into perspective in a very practical way, I've picked a delta. I don't know if all of you know this one. It's called the Ebro Delta in southern Spain. And in this diagram in 1908, the red areas show the area of the land that is impacted by a reservoir. So only 3% in southern Spain, 1908. It went up to, in 1960, it went up to 22%. In 1990, we had 71%. And of the Ebro, 95% of the river was, river flux and river basin was impacted by a multitude of dams. So if you looked at the discharge, it went down by a factor of 5 or more. And if you looked at the sediment load, it was decreased by 2 orders of magnitude. And humans being humans, and geoengineering as geoengineering is, we now replace this sediment by trucking sediment back to the delta. We have a river of trucks, and particularly in this area there's salt pans, and these salt pans, there's a road that connects it through here, and they have to rebuild this road every year, and they're just trucking sediment rather than letting the river do its thing. So we have global models now that can capture this, and this is an example of one of these global models. It's called the WBM SED, and you can see the Nile River picking up sediment along the way. It hits this reservoir, and this dirty water gets cleaned up, and so you have clean water that leaves the system. And so if you were to look on a global basis through this model, you don't need to know much about it, but it takes into account, are there glaciers in your drainage basin? What's the lithology of the rocks? What's the discharge, the size of the river system and area? What's the relief and temperature? And before humans got there, we were kicking out about 15 gigatons of suspended sediment. Again, that's been reduced to the coastal ocean mostly because of this trapping. And here it doesn't look like a big magnitude because we're balancing rivers that have been made dirty by humans with rivers that have been made clean by humans. But if you were to look on an individual basis, you can see, and I picked some ones that you may recognize. In terms of mean discharge, we have changed much of the flow to the ocean, the maximum flood events, the suspended load of sediment, and the water turbidity, the sediment concentration. So let me just summarize this part. So we're stirring up the hinterland, and we're capturing much of that stirred sediment these days in the reservoirs itself. Each river system is a snowflake. They have their own story. It's hard to make generalizations because of this, but as you can see, it's a global phenomenon. So let's get to deltas. So let's start with the world population. Things are only being greater impacted in our coming future. We're getting approximately 1 million people every 10 days for the next century. And much of this growth is occurring on megacities on deltas. And I have a list of these megacities, then their deltas. And in 1975, there's their population. It's increased so that in 12 delta cities have gone from 62 million in 1975 to 153 million. So this next story is a story related to them. Oops. So, if you were a person living on a delta, you're interested in this bouncing ball. Where's the sea compared to the land surface. And you've got the following factors affecting your life. The ocean volume may increase. You may be adding sediment so that you've got aggradation. There's some geological processes that may lower the system. You're naturally compacting the sediment, and you may artificially compact the sediment. So you have this simple equation, and if we put some numbers beside these factors, let's start with a natural hypothetical delta, that the aggradation rate was 10 millimeters per year, sea level was not rising that fast, maybe 0.5 millimeters per year. Natural compaction we're going to hold constant. Isostasy we're going to hold constant, and since there were no humans, accelerated compaction, 0. You then decrease the amount of sediment, increase this sea level rise, and increase this accelerated compaction, and all of a sudden you have a shrinking delta. And if you look at the deltas of the world, they're sinking 4 times faster than sea level is rising. So if you're a person living on a delta, you're more concerned about what humans are doing below the land surface. And all these areas in pink are areas below sea level. And here's some other examples of areas below sea level that are controlled from the ocean simply by embankments. And this is another set of deltas that show areas that are less than 2 meters above sea level, to give you an indication of how fast we may be impacting world delta systems. If we looked at a series of deltas and we were looking at the areas below sea level, we've already got close to 30,000 square kilometers of area on Earth below sea level. And you can almost double that in the areas that are close to sea level, less than 1 meter, and the less than 2 meter, you're up to 87,000. But when people do this bathtub, just raising sea level, they're forgetting the dynamics. The dynamics are that if you look in the last decade, 85% of these deltas have flooded, and the flooding area is 260,000 square kilometers. That's a much larger area than the area that's simply close to sea level. And that's because storm surges lift the water many meters above the land. So when you're looking at, this is a paper by Bloom and Roberts, and you can see where the predicted 2100 coastline of New Orleans is. This is, again, not looking at the dynamics of such things as hurricanes. So let's look at accelerated compaction, because you need to know this story. Methane mining on the Po Delta, sinking it at 60 millimeters per year. Venice did not like that. They were sinking too fast. So they stopped that mining, and there was recovery down to 20 millimeters per year just a few years later. And now in the 1990s, you're back to close to ambient, 4 millimeters per year sinking. So we know what we are able to do, and we know when we stop doing that, what the recovery rate would be. Students of mine have been looking using interferometric synthetic aperture radar or persistent scatter INSAR, and they've been looking in details on these deltas. What's causing the sinking? In the yellow delta, a fish farm growing tonguefish, these flat fish, they have to pump up seawater and replace the water every 10 days. They have to pump up so much water. They're sinking the delta area by 1 meter in 4 years. That's incredible, creating wetland erosion all along the yellow delta. You have areas of Jakarta, a slide from Deltares showing 4 meters below sea level. You have the Chalfreya sinking at 100 millimeters per year due to water extraction. The Netherlands, due to peat compaction and peat oxidation, you have a quarter of the country below sea level. You're cutting down the mangrove forest at enormous rates. So along the Chalfreya, you're having erosion of up to and exceeding a kilometer over the last few decades. And to give you an example of what that would be like, here's an example of the Chalfreya. 2001, 250 meter scale bar. Just a few years later, you're having 250 plus meters of erosion in locations. You cut the mangroves, you have these extremely flat surfaces for shrimp farming, and you have rapid erosion. The Indus Delta that doesn't get any water and sediment anymore, this is a map between 1935 and 2000, and all the area in yellow is eroded land surface in square kilometers. Over 1,000 square kilometers of land have been eroded. Just some deposits near the river mouth, the modern river mouth. So we're rapidly eroding these delta systems around the world. These, unfortunately, are the major food baskets, rice bowls of the world. And what happens on them, whether the flooding be from the river or from the ocean, really impacts the food supply. And believe me, anything that happens there impacts the U.S. We're part of the story, so it's not a them thing, it's an us thing. So if you were to look at how these deltas behave, these three stars, blue, yellow, and red on the Ganges, you can have parts of the delta system that receive water and sediment from the river and can agrade. You have river systems that are connected to the tidal channels and receive sediment, but you have more and more areas that are disconnected because of salinity conditions, that they only receive water from the sky, rainfall. And therefore they are sinking and there's no new sediment that gets on top of them. And the farming there, of course, is with these oxen. In the Netherlands, they are using heavy tractors, therefore they have to pump dry their delta system, and because of their pumping dry on an annual basis, they're oxidizing the sediment. The peat, I should say. Often because of these lowlands, floods will bring in lots of sand. These sands carried in by a cyclone, a typhoon, a hurricane, will render these areas useless to the farmers. Where they once could grow rice, they can no longer grow rice. And of course, when you throw all these artificial structures and you have normal river dynamics, they quickly and more acceleratedly erode through the system. So, let me summarize this talk. Our global footprint needs to be understood. And with this understanding, I think we can better develop the policies and practices that can support global sustainability. You know, we've had some great successes. So when we talk about reservoirs and deltas, we put these in for very good reasons, but we haven't been that aware of the consequences down the road decades later. So we've had successes and we've had failures. And when we start thinking about geoengineering our atmosphere, all I can say, based on past history, is that I think we might have some successes, but likely we will also have failures. Thank you.
We have time for a question or two. It's hard to see. If you have one, step up to the mic because we can't see you from here.
Oh, there's one.
Hi, thank you. I really enjoyed your talk. I don't know if I'm too close to this thing. Could you talk about what your take on dam removal is?
Could you say that again? Repeat
Sure.
that.
Can you talk about your take on dam removal?
Oh, okay. Yeah. So, two aspects of dam removal. We're removing dams at too slow a rate compared to what we're building. So, dam removal is not going to change the story too much. When the removal goes on, and the U.S. is the leader in this, you will pump down a lot of sediment to the coastal ocean. That sediment, some of it will get there within weeks, months. Sometimes that sediment may take years, depending how far upstream the dam removal will be. But you could replenish the system. The unfortunate thing is the flux of the sediment will be moved at such a high rate that you will likely, for the short term at the very least, be harming the wetlands rather than helping them. But eventually they will recover, hopefully. Yeah, so the San Francisco San Joaquin Delta system, one of the largest in the world. It's sinking rapidly. Its infrastructure is failing constantly, and unless we put in tens of billions of dollars to repair that system, we're only going to have more and more disasters, as we have had in the last 10 to 20 years. So the crevasse splays and breaks in the levee systems are on a rather constant basis. We can't engineer that system, it's too large. Okay.
Please join me in thanking James Syvitski for being our plenary speaker today.